Radiometric dating involves the decay, or nuclear transmutation, of an unstable parent nucleus into a stable daughter nucleus. The amount of parent and daughter nuclei present reveal how long a sample has existed. Half-life is the amount of time it takes for half of the existing amount of parent nuclei to decay into daughter nuclei. After one half-life, half of the initial parent has decayed. After a second half-life, half that remaining amount has decayed. After 3 half-lives, half of that, etc. To calculate the age, one needs to know what the starting amount of parent and daughter nuclei were and what the current amounts are. One also needs to know what the half-life of the parent nuclei are. Shown here are some common unstable isotopes. Their half-lives range from fractions of a second to billions of years. The parent nucleus that is used to determine the age of the solar system is potassium-40. It has a half-life of 1.25 billion years. This graph depicts a general decay process. The graph of the amount of parent nuclei is shown with the blue curve and the amount of daughter nuclei is shown in red. Note that there are no daughter nuclei present initially. This is often not the case, and the dating process is sometimes a bit more complicated. For the decay process that will be discussed in this class, there will be no daughter nuclei present when the rock forms. Considering only the nuclei relevant to this particular decay process, it starts with 100% parent nuclei. On the horizontal axis is basically time, measured in half-lives of the parent nuclei. The vertical axes show the percentages of the nuclei present. The sum of parent plus daughter will always add up to 100%. After one half-life, 50% of the parent has decayed to daughter. Therefore, there is then 50% parent and 50% daughter nuclei. After 2 half-lives, only 25% of the nuclei are still parent and 75% are daughter, etc. In practice, we don't know for how many half-lives a sample has existed. That is what we are trying to find out by measuring the relative amounts of parent and daughter nuclei now present in the sample. Suppose you are going to use a decay process to date a sample and that the parent nuclei have a half-life of 1 billion years. Imagine you measured the amount of parent and daughter nuclei present in a sample and found that 87.5% was daughter. How old is the sample? Looking at the vertical axis for the daughter particle percentages, we would go up to 87.5% and from there, move horizontally to the curve representing the amount of daughter nuclei. This is shown by the horizontal green arrow. We know that this point on the curve must represent where the decay process is at this time. We then move from there to the horizontal axis and read off the number of half-lives. This is depicted by the vertical green arrow. We find that the sample has existed for 3 half-lives. Since we know the half-life is 1 billion years, we then simply take 1 billion times 3 to get the age of the sample. Thus, the sample is 3 billion years old. As another example, suppose we were given the amount of parent present, rather than the amount of daughter. Imagine that we were told that the sample contains 6.25% daughter nuclei. We do the same process, only using the parent axis and the parent curve, as shown with the purple arrows. We would find that the sample has existed for 4 half-lives and that its age was 1 billion times 4, or 4 billion years. This graph shows the decay of potassium-40 into argon-40. Recall that potassium-40 has a half-life of 1.25 billion years. When the solar system is forming, all elements and compounds begin in a gaseous state, then slowly form solids. Argon is what is referred to as a noble gas and will not congeal with other atoms when a crystal forms. Thus, the starting amount of argon-40 is 0%. The starting amount of potassium-40 must be 100%. Any argon-40 found later in the sample must have come from the decay of potassium-40. By measuring the relative amounts of potassium-40 and argon-40 currently in a rock, we can determine the number of half-lives it has existed for and thus how old it is. If anything happens to the rock to cause the argon-40 to escape, like massive collisions or remelting, this resets the radiometric clock. Rocks on Earth go through a rock cycle where rock is continually being remelted and new material brought to the surface to form new rock. Thus, we cannot use Earth rocks to date the age of the solar system. We use primitive meteorites. These are meteorites where nothing has occurred to reset their radiometric clocks. Dating these types of meteorites gives a consistent age for the solar system of 4.6 billion years.